Okay, looking at number 4 here, it's going to turn out that the math we end up doing is not all that complex, but to see that, I'm actually going to start with just a standard ICE table. Now, something I do when I'm writing out my ICE table is I actually plan something when I'm rewriting it kind of in my head. And what I'm noticing is I had a solid right there. So what I'm going to do is when I actually start making my ICE table, I'm actually going to put a dash right there. Because the reason I'm using a dash is because solids never pop up into my Q's. And that's because they won't have a variable concentration. Their concentration is more related to their density, and it's rigid as a solid, so it doesn't change. So I'm putting that there to remind myself not to put it into my Q equation, but also to remind myself that its concentration will never matter. We can flat out ignore it for this problem. So even though this thing tells me that I put 1.52 moles in there, the only thing I need to do scientifically is realize that it's there. It is going to allow this reaction to go into equilibrium, and since I didn't mention anything about these two, they must be at 0. So this is going to drop. The moles will drop. It's just the concentration won't drop. But at equilibrium, we have just this X and X, and this doesn't matter. Because no matter what, even though the amount drops, the concentration would not. Alright, so here's where this gets to be very nice. These values I gave, the 8.44 is the amount of pH3 at equilibrium, and it's the moles. Well, those would be the same because this 8.44 times 10 to the third came from that 0.152. So both of these would be at that 8.44 times 10 to the third. So to figure out my K in this case, I'm just going to take that value. Remember, these concentrations need to be that. They need to be concentrations. So I'm going to divide it by the volume. And technically, I'm going to do that for the BCl3 as well. And multiplying those two together, which would be our X's, is going to give us our K. And I can just square that, and I end up with a K of 7.91 times 10 to the negative 6th.